Hello friends, in this lecture we shall study about mechanism of organic reactions. In that we shall focus on the important factors responsible for determination of mechanism of reaction. They are product analysis, crossover experiments, stereochemical evidences, use of isotopes, kinetics of reaction, detecting and trapping of intermediate. So first we shall see how product analysis helps us to determine the mechanism of reaction. In past, this product analysis had to be done laboriously and often imprecisely by manual isolation of products, but now often be achieved more easily and precisely by making use of sophisticated chromatographic methods or indirectly by suitable spectroscopic techniques. Now, how product analysis is important in determining mechanism of reaction that we'll understand by considering this example. Triphenyl methyl chloride in presence of silver gives yellow color triphenyl methyl radical, and further it undergo dimerization to form colorless hexaphenyl ethane with 30 aromatic hydrogen atom. After 70 years, in 1968, the dimer was subjected to NMR studies and it was found that it contains only 25 aromatic hydrogen atom, 4 dienic hydrogen atom and 1 saturated hydrogen atom, and this leads to the fact that compound, that dimer, was not hexaphenyl ethane, which leads to different mechanism and not through dimer formation. In this case, one triphenyl methyl radical gets rearranged itself and combined with other triphenyl methyl radical to get this desired product. Now we shall understand the importance of product analysis by considering another example. We know that chlorobenzene is readily converted into aniline in presence of soda amide in liquid NH3 at -33 degrees Celsius. But when parachloromethylbenzene undergoes same reaction, it not only gives the expected product, that is para-aminomethylbenzene, but it also gives the unexpected product, that is meta-aminoethylbenzene. Here, the presence of only one product, that is para-aminomethylbenzene, suggests that reaction proceeds through simple aromatic nucleophilic substitution reaction, but the presence of unexpected product, that too in larger amount, demands for another mechanism. Here, the loss of proton from parachloromethylbenzene followed by loss of chloride ion to give arine intermediate. It is then possible for the molecule of solvent, that is NH3, to adds on to this arine intermediate in either of the two different ways around to give two different product, that is para-aminomethylbenzene as well as meta-aminomethylbenzene. Here we would not, however, expect to obtain these two alternative products in equal proportion, as the intermediate, that is arine intermediate, is not symmetrical and the presence of methyl substituent might well be expected to influence the orientation of NH3 addition. Hence, the presence of two products suggests that reaction follows arine pathway and does not proceed through aromatic nucleophilic substitution reaction pathway. Next is crossover experiments. Crossover experiments are particularly useful in studying the reaction mechanism of many molecular rearrangements. In crossover experiments, a mixture of starting material that differ from each other only in one characteristic group is applied. The structure of product is then obtained, which tells us whether or not an intermolecular exchange of atoms or a group of atoms has occurred. We shall understand the importance of crossover experiments by considering the example of pinacol-pinacolan rearrangement. When 1,2-diol gets converted into highly substituted carbonyl compound under acidic condition, it is known as pinacol-pinacolan rearrangement. But when a mixture of diols was subjected to pinacol-pinacolan rearrangement, it was observed that crossing of methyl and ethyl groups were not observed. That is, such products were not obtained. This suggests that reaction proceeds through intramolecular rearrangement, that is, group of atoms rearranges within the same molecule. Another example is benzidine rearrangement. If a mixture of starting material containing 2,2-dimethoxyhydroazobenzene and 2,2-diethoxyhydroazobenzene is applied to benzidine rearrangement, a product mixture that consists of two symmetrically substituted benzidines is obtained. Thus, the reaction obviously takes an intramolecular course. Otherwise, unsymmetrically substituted benzidines must also be formed. So with the help of this crossover experiments in pinacol-pinacolan rearrangement and benzidine rearrangement, it suggests that rearrangement is just an intramolecular rearrangement, which in turn helps to determine the mechanism of reaction very easily. Next is stereochemical evidences. Information about the stereochemical course followed by a particular reaction can also provide useful insight into its mechanism and may introduce stringent criteria that any suggested mechanistic scheme will have to meet. Thus, the fact that the base catalyzed bromination of an optically active isomer of ketone leads to an optically inactive racemic product. Racemic product means mixture of dextro and levo in equal amount, which indicates that reaction must proceed through a planar intermediate, which can undergo attack equally from either side, that is either from front side or from back side, leading to equal amount of two mirror images form of the product, that is dextro and levo. So in this case, the final product obtained is a racemic mixture, which in turn suggests that intermediate form is a planar, and this information is useful while determining mechanism of reaction. Next is kinetics of reaction. The kinetic studies give lot of information which may lead to the possible pathway of the reaction. The rate of reaction is the rate at which reactant disappear or product appears at a particular temperature, and the rate of reaction is found by noting the changes in concentration, color, conductivity or any other property which changes with time. For example, in alkaline hydrolysis of primary alkyl halide, the rate of reaction depends on the concentration of both the alkyl halide and the nucleophile. This in turn suggests that both alkyl halide and nucleophile are simultaneously involved in the same step. This results in the transition state, which then changes to product. So from this mechanism, it is easy to understand that why rate of reaction depends on the concentration of above two species. However, in alkaline hydrolysis of tertiary halide, the rate of reaction depends only on the concentration of alkyl halide, but is independent of the concentration of nucleophile. Thus, both alkyl halide and nucleophile are not involved in the same step. Thus, it must be a two-step reaction. According to the principle of kinetics, in multi-step reaction, the slowest step is called the rate limiting step, and the overall rate of reaction depends on this step. Therefore, the slowest step is also called the kinetic bottleneck in the path of reaction. Hence, from the above two steps, it is easily concluded that rate of reaction depends on the concentration of only alkyl halide and does not depend upon the concentration of nucleophile. Next is use of isotopes. In this, we shall see that how use of isotopes helps in determining mechanism of reaction. Many a times we need to know whether a specific bond breaks during the rate limiting step or in another step. This information cannot be obtained by a simple kinetic data. The isotopes have been used in determining these finer aspects of reaction mechanism. The commonly used isotopes are stable isotopes like carbon 13, nitrogen 15, oxygen 18, etc. And this can be detected by mass spectrograph or by infrared spectroscopy. Whereas radioactive isotopes can be detected by GM counter, for example carbon 14, phosphorus 32, iodine 131, etc. The isotopes are usually used as tracers. Thus, the starting material is labeled at a particular point, and after the reaction, the labeled atom is located in the product. We know that when acid and alcohol react with each other, it gives us ester and water molecule. But the question arises that oxygen atom present in water molecule or in ester molecule comes from which starting material, that is either from acid or alcohol. Here we can get rid of this dilemma if the reaction is carried out with an oxygen labeled alcohol, that is 18 oxygen labeled alcohol. In the end of the reaction, the 18 oxygen isotopes is exclusively found in the ester and not in the water. This in turn indicates that a nucleophile attack of alcohol's oxygen atom on the carboxylic acid carbonyl group has occurred, and that the alcohol proton has subsequently been cleft off during the mechanism. We know that higher the activation energy, lower is the reaction rate as well. Therefore, the overall reaction rate can be increased by lowering the energy of activation of a rate determining step. But if we reduce the energy of activation of non-rate determining step, it does not influences the rate of reaction. That is, the rate of reaction does not changes if we decrease the energy of activation of non-rate determining step. Suppose XH bond is cleaved during rate determining step, and if hydrogen is replaced by deuterium, that is isotopes of hydrogen, so it is heavier than hydrogen atom, so it requires more energy to cleave this bond. If it requires more energy, it indicates that energy of activation is high. If energy of activation increases of the rate determining step, then the rate of reaction is decreased. This effect is known as primary kinetic isotope effect. So in short, we can say that when the overall reaction rate is decreased by the exchange of an hydrogen for a deuterium from the XH bond that is cleaved during the rate determining step, this effect is known as primary kinetic isotope effect. The cause of this effect is the elevation of activation energy of rate determining step arising from hydrogen deuterium exchange. Usually, the larger the relative mass difference between the isotopes of respective element is, the larger the kinetic isotope effect is observed as well. The largest kinetic isotope effect are therefore found when hydrogen atom is exchanged for deuterium and even for tritium. There are different types of kinetic isotope effects. The numerical quantity of kinetic isotope effect is expressed by the ratio of rate constant, that is Kh upon Kd. Kh is rate constant when hydrogen is present and Kd is rate constant when deuterium is present. The value of Kh upon Kd can amount up to 7. If a CH or CD bond is cleaved during the reaction, then that effect we call it as primary kinetic isotope effect. And if CH or CD bond is not cleaved during the rate determining step, then the reaction is called as secondary kinetic isotope effect, and this effect is usually smaller, that is ratio of Kh upon Kd is smaller than 2. In case of secondary kinetic isotope effect, Kh upon Kd can also become smaller than 1, that is the reaction rate is then lower with hydrogen than it is with deuterium, so we call it as inverse secondary kinetic isotope effect. Now, depending on the distance between isotope and the actual reaction center, the secondary kinetic isotope effect can called be alpha, beta or gamma secondary kinetic isotope effect. The alpha secondary kinetic isotope effect can additionally be classified as normal alpha secondary kinetic isotope effect, where Kh upon Kd is greater than 1. In the case of this effect, the reaction rate is reduced. And next is inverse of secondary kinetic isotope effect, where Kh upon Kd is less than 1. In the case of this effect, the reaction rate increases. Next is detecting and trapping of intermediate. Now we shall see how it is useful in determining mechanism of reaction. If an intermediate product is stable enough or its lifetime is sufficiently long and its concentration is high, then its isolation and subsequent structure elucidation may be possible. For this purpose, it may be necessary to arrest the reaction through rapid cooling to a very low temperature. Or at least the reaction rate must be reduced so that the intermediate product is not noticeably converted into the final product during the measuring process. At this point, evidence is needed that the isolated compound is actually an intermediate and not a side product. The intermediate are often not capable of being isolated, as they are not stable enough or they are otherwise too low in concentration. In such cases, an attempt may be made to trap the intermediate with suitable interceptor. However, in some cases, the formation of intermediate can be directly established by trapping experiments with suitable reagents and establishing the structure of the resultant product. For example, during Riemann-Timan reaction, dichlorocarbene may be formed as an intermediate, and the formation of dichlorocarbene can be established by trapping with an alkene like cis-2-butene. Similarly, when chlorobenzene is treated with soda amide and liquid ammonia, the reaction follows elimination-addition mechanism involving formation of benzyne intermediate. When small amount of furan is added, the benzyne is trapped and the product on treatment with acid gives alpha-naphthol. This confirms the formation of benzyne. Hence, we can say that by trapping the intermediate, it may help us to determine the mechanism of reaction.